This is the reason distant galaxies are moving away from us faster than light can ever cross the gap, and why huge sections of the universe are already gone from us forever, even though nothing has physically exploded, collided, or been destroyed. Space itself is stretching, right now, while you listen to this sentence, and it has been stretching for close to 14 billion years. If this kind of deep dive into the mechanics of reality keeps your brain hooked the way it hooks mine, go ahead and hit like on this video and subscribe to the channel, because there is a lot more of this coming. Here is the plain version of what is happening. The universe is not expanding into some larger empty room the way smoke fills a garage. There is no outer wall it is pushing against. Instead, the distances between galaxies are growing, everywhere, all at once, the same way the surface of a balloon stretches when you blow air into it. Except, there is no surface, no edge, no center you could point to and say, that is where it all started. Every galaxy, roughly speaking, sees every other galaxy rushing away from it, and the farther away a galaxy sits, the faster it appears to be receding. Before we go further, one quick unit worth having in your back pocket, since we're going to be using it constantly. A light year isn't a measure of time, despite the name, it's a measure of distance. Specifically, the distance light travels in a single year, moving at roughly 186,000 miles every second. That works out to something like 6 trillion miles packed into a single light year. When astronomers say a galaxy sits 10 billion light years away, they mean the light reaching our telescopes tonight left that galaxy 10 billion years ago and has been crossing an ever-growing gulf of space ever since. Every distance in this video is really a window into the past, a snapshot of how something looked at the exact moment its light started its journey toward us, not how it necessarily looks right now. Even something as close as the moon shows this effect on a tiny scale. Its light takes about 1¼ seconds to reach us, and sunlight takes about 8 minutes, meaning you never actually see the sun as it is right now, only as it was 8 minutes ago. Push that same idea out across billions of light years, and you start to see just how deep into the past our telescopes are really looking. That relationship, distance predicting speed, has a name. It is called Hubble's law, and it comes with a number attached to it, a number astronomers call the Hubble constant, written as h0. The Hubble constant tells you how many kilometers per second faster a galaxy recedes for every additional megaparsec of distance between it and us. And a megaparsec, if you are curious, works out to roughly 3.26 million light years. Or to put that in perspective, our nearest large galactic neighbor, Andromeda, sits about 2/3 of a megaparsec away. So we're talking about distances that make even our closest galactic neighbors look like a rounding error. So when a cosmologist says h0 is about 70, what they mean is that a galaxy sitting 1 megaparsec away is drifting from us at about 70 kilometers every second. A galaxy 2 megaparsecs away is drifting at about 140 kilometers per second, and the pattern keeps climbing the farther out you look. Here's the thing that makes this genuinely strange, rather than just a tidy formula. Push that relationship out far enough, to galaxies billions of light years away, and the implied recession speed eventually crosses the speed of light itself. That sounds like it should break physics. It does not, and the reason it does not is the same reason nothing about this is actually a violation of Einstein's rules. Objects are not zooming through space faster than light in any local sense. The space between us and them is what is expanding, and general relativity places no speed limit on how fast space itself can stretch. A rocket cannot outrun a beam of light. The universe apparently can. Let's slow down on that balloon comparison for a second, because it trips people up more than almost anything else in cosmology, and it's worth getting right before we go any further. Picture dots drawn on the surface of a balloon, representing galaxies. And now picture that balloon slowly inflating. Every single dot moves farther away from every other dot, not because any dot is crawling across the rubber surface towards some destination, but because the rubber itself, the space between the dots, is stretching. Pick any dot you like and treat it as your home base, and from that dot's point of view, every other dot appears to be receding, and the farther away a dot sits, the faster it appears to pull away, purely because there's more stretching rubber between you and it. No dot is special. No dot sits at the center. Every single point on that surface would see exactly the same pattern if it were the one doing the observing. That is, as close as a physical object can get, a working model for what cosmologists mean when they say space itself is expanding. And it's why there was never a single central point where the Big Bang happened that we could point a telescope toward. The Big Bang happened everywhere, all at once, including right here, because everywhere was, at that moment, the same infinitesimally small place. Now bring redshift back into that picture. Light is a wave, and just like sound waves get stretched when their source pulls away from you, dropping an ambulance siren from a high pitch to a lower one as it passes and speeds off, light waves get stretched toward longer wavelengths when their source is receding. Longer wavelengths of visible light sit toward the red end of the spectrum, so astronomers call this effect redshift, and the amount of stretching tells you, mathematically, how much the space between the source and the observer has expanded since the light was emitted. This is subtly but importantly different from an object simply moving away from you through static space, the way a car pulls away from a curb. In an expanding universe, the light itself is being stretched by the growing distance it travels through, continuously, the entire time it's in transit, which is exactly why light that left a galaxy when the universe was young can arrive here billions of years later, stretched into wavelengths its original source never actually emitted. One question this naturally raises is why, if space itself is stretching everywhere, you and this planet and the entire solar system aren't slowly stretching along with it, quietly ballooning outward at some imperceptible rate? The answer comes down to a simple contest of strength. Cosmic expansion is an extremely weak effect over any small distance, and it only adds up to something significant over genuinely enormous stretches of space, hundreds of millions or billions of light years. Even across a distance as large as the gap between the Earth and the Sun, the outward pull from cosmic expansion amounts to something so small it would take many times the current age of the universe just to stretch that distance by a width you could actually measure. On the scale of a solar system, or a galaxy, or a person, the ordinary forces holding things together, gravity binding planets to stars, electromagnetism binding atoms into molecules, the nuclear forces binding atomic nuclei together, are all overwhelmingly stronger than the outward pull of cosmic expansion at that scale. Space might technically be trying to stretch everywhere, including inside your own body, but the forces holding you together win that contest so completely it isn't even close. It's only once you get out to the vast, mostly empty gaps between galaxies, regions with essentially nothing gravitationally binding them together across such enormous distances, that expansion's cumulative effect finally wins out and becomes the dominant force in play. That single idea, quiet as it sounds, is the reason huge stretches of the cosmos are permanently, unrecoverably out of reach. And it's the reason astronomers can now say with a straight face that there are parts of the universe we will never see, never detect, and never receive so much as a single photon from, no matter how long humanity survives, or how advanced our instruments become. Before any of that could be measured, though, somebody first had to solve a much more basic problem. How do you even know how far away a galaxy is in the first place? Redshift alone only tells you speed. It tells you nothing about distance on its own. And the person who quietly solved that half of the puzzle almost never gets her name mentioned in the popular version of this story at all. Her name was Henrietta Leavitt, and she worked at the Harvard College Observatory in the early 1900s, one of a group of women, sometimes remembered today as the Harvard Computers, hired by observatory director Edward Pickering at a fraction of what a man would have been paid at the time, to perform the painstaking, detail-heavy work of cataloging and measuring stars from photographic plates, work that the observatory's male astronomers generally considered beneath them. Leavitt eventually rose to head the observatory's photographic stellar photometry department, spending years examining those plates by hand, cataloging variable stars in two small satellite galaxies of the Milky Way called the Magellanic Clouds. In 1908, after studying more than 1,700 of these variable stars, she noted something simple but important, that the brighter variables tended to have longer periods, longer cycles of pulsing brighter and dimmer. By 1912, working with a refined sample of 25 Cepheid variable stars specifically, she nailed the relationship down mathematically. Because all 25 of those stars sat roughly the same distance from Earth, tucked inside the same small satellite galaxy, any difference in how bright they appeared had to come from genuine differences in how bright they actually were, not from some of them simply being farther away than others. That let her isolate a clean, direct relationship between a Cepheid's pulsation period and its true, intrinsic brightness. Time how long a Cepheid takes to pulse, and you now know how bright it actually is. Compare that true brightness to how dim it appears from Earth, and you can calculate exactly how far away it sits. It's the same basic logic later used for supernovae, knowing the true wattage of a light bulb and judging distance purely by how faint it looks from across a field. Except Leavitt worked this out roughly 90 years before anyone would use the same trick on exploding stars. Leavitt's period luminosity relationship, now formally called the Leavitt law, became the very first rung of what astronomers still call the cosmic distance ladder, and it is the tool Edwin Hubble used to measure the distance to the Andromeda galaxy, the first time anyone had ever measured the distance to a galaxy outside our own, and it's the same basic method, refined again and again over a century, that the SH0ES team still leans on today in their modern Hubble constant measurements. Leavitt died of cancer in 1921, and in a detail that says something quietly devastating about how overlooked her work was in her own lifetime, a member of the Swedish Academy of Sciences attempted to nominate her for a Nobel Prize in 1924, 3 years after she had already died, unaware that she was gone. Nobel Prizes cannot be awarded posthumously, so she never received one. A century later, in 2025, researchers went back through Leavitt's original handwritten notebooks and reanalyzed her actual measurements using modern techniques, and found that her original 1912 calculations held up remarkably well, in excellent agreement with what modern instruments produce, off by a margin far smaller than anyone had a right to expect from data gathered by hand, off photographic plates, more than 100 years ago, using an eye trained on nothing more sophisticated than a magnifying glass and sheer, patient repetition. We're going to walk through how we found out the universe is expanding in the first place, why two completely different ways of measuring that expansion give two different answers that still refuse to agree with each other, why the expansion itself appears to be speeding up rather than slowing down, and what all of this means for how far the universe stretches beyond what we can ever follow. The story usually gets told with one name attached to it, Edwin Hubble, but the real history is messier and honestly more interesting than the shorthand version. Long before Hubble published anything, an American astronomer named Vesto Slipher had already been quietly measuring something called redshift in distant spiral nebulae, which is what astronomers used to call galaxies before they understood what galaxies actually were, working alone for years at Lowell Observatory in Arizona, an institution founded in 1894 by the wealthy businessman Percival Lowell, who was personally far more interested in searching for supposed artificial canals on Mars than in the redshifts of faint spiral nebulae, an obsession now considered a historical footnote of astronomy, but one that, almost by accident, built the observatory and funded the instruments Slipher needed for entirely different, much more consequential work. Slipher used a spectrograph attached to a telescope, painstakingly capturing enough light from these faint, fuzzy patches to break it apart into a spectrum and measure exactly how far its features had shifted. Redshift happens because light stretches toward longer, redder wavelengths when its source is moving away from you. The same basic principle behind why a passing ambulance siren drops in pitch as it speeds off. Slipher found that nearly every nebula he studied showed this stretching, meaning nearly everything out there appeared to be moving away from Earth, some of them receding at speeds of hundreds, even over 1,000 kilometers per second, startling numbers for the era. What nobody had yet was a clean way to connect those velocities to actual distances, and that's where the story gets crowded. Slipher's measurements alone had taken years of patient, unglamorous effort, each spiral nebula requiring hours of exposure time through the cold Arizona night just to gather enough faint light for a single usable spectrum, the kind of slow, invisible groundwork that rarely makes it into the popular retellings, but without which none of what follows in this story would have been possible at all. A fitting first chapter for a discovery that would go on to define the rest of humanity's understanding of everything. In 1922, a Russian mathematician named Alexander Friedmann worked out something remarkable using Einstein's own equations of general relativity. The math allowed for a universe that was not fixed in size, one that could expand or contract over time. Einstein himself, at that point, still believed the universe was static, eternal, and unchanging, and he had gone so far as to insert an extra term into his own equations, something called the cosmological constant, specifically to cancel out any expansion or contraction and force his math to describe the still, permanent cosmos he assumed was real. Friedmann's work suggested Einstein's fix wasn't necessary at all, and that a dynamic universe was allowed by the very equations Einstein had written down himself. It's worth sitting with that for a second, because the man who built the entire theoretical framework this whole field rests on initially refused to believe what his own equations were telling him, and patched them specifically to avoid a conclusion that later turned out to be correct. Once Hubble's observations forced the issue, Einstein dropped the extra term, and the whole episode became one of the most talked about course corrections in the history of physics, precisely because decades later, that same cosmological constant would come roaring back into relevance as one of the leading mathematical descriptions of dark energy itself. There's a famous quote attached to this whole episode, the claim that Einstein privately confessed the cosmological constant was the biggest blunder of his life. It's worth being honest about where that quote actually comes from, because the story is shakier than most retellings let on. The line traces back to a single source, the physicist George Gamow, who claimed Einstein said it to him directly, first mentioning it in a 1956 magazine piece and later repeating it in his own autobiography. No written record of Einstein ever saying anything like it has turned up in his own papers, and Gamow, by most accounts, had a well-earned reputation as a prankster and a storyteller, which has left historians genuinely divided over whether Einstein ever said those exact words at all. Two other physicists did separately claim to have heard Einstein make a similar remark, which keeps the story from being dismissed entirely, but the honest answer is that we can't be fully certain. What we can be certain of is this: Einstein introduced the term to force a static universe out of his own equations. He abandoned it once Hubble's data made a static universe untenable, and that same abandoned term became essential again the moment scientists needed a way to mathematically describe a universe that wasn't just expanding, but accelerating. Blunder or not, quote or no quote, the irony writes itself. While we're untangling terminology, it's worth clearing up a mix-up that trips up a lot of people encountering this material for the first time, the difference between dark matter and dark energy, because the similar names make them sound like the same mystery when they're actually two completely separate ones. Dark matter was first inferred back in 1933 by Swiss astrophysicist Fritz Zwicky, studying a cluster of galaxies called the Coma cluster at Caltech, who found the cluster's galaxies were moving far too fast to be held together by the gravity of the visible matter alone, and coined the term dunkle materia, dark matter, for whatever invisible mass was providing the extra gravitational glue. Zwicky had a reputation in his own lifetime as a brilliant but famously prickly colleague, quick to accuse other astronomers of stealing his ideas, and his dark matter proposal sat largely ignored for decades, treated more as an eccentric footnote than a serious puzzle, until rotation curve studies, decades later, forced the field to take it seriously. Decades later, in the 1970s, astronomer Vera Rubin, working with Kent Ford, found the same basic problem showing up again and again while studying how fast stars orbit within individual spiral galaxies, using painstaking spectroscopic measurements of dozens of galaxies over years of observation. Stars out at the edges kept moving at speeds that should have flung them off into space entirely, unless something invisible, spread out well beyond where the visible stars end, was adding enough extra gravitational pull to hold everything together. Rubin's meticulous, repeated confirmations across galaxy after galaxy are largely what turned dark matter from an obscure, decades-old curiosity of Zwicky's into a serious mainstream problem the entire field had to reckon with, and the ground-based observatory recently built in Chile to hunt for exactly this kind of large-scale cosmic structure, the same Vera Rubin Observatory mentioned earlier in connection with the Yonsei and Southampton debate, now carries her name. That same rotation curve pattern repeated across essentially every large galaxy ever studied in detail, is a big part of why dark matter's existence is taken so seriously despite nobody ever having directly detected a single particle of it. It's worth being fair and mentioning that dark matter isn't the only explanation anyone has ever proposed for these odd galactic rotation speeds. In the early 1980s, Israeli physicist Mordechai Milgrom, working at the Weizmann Institute, proposed an alternative called modified Newtonian dynamics, or MOND, which suggests that instead of invisible extra mass, our basic laws of motion themselves might behave slightly differently at extremely low accelerations, the kind found way out at the edges of galaxies, than they do here in the solar system. MOND does a genuinely good job predicting certain patterns in how galaxies rotate, which has earned it a small but persistent following. But it's very much a minority position among working astronomers, and more recent evidence, including detailed studies of wide binary star pairs using data from the Gaia satellite, and observations of colliding galaxy clusters like the famous Bullet cluster, where the gravitational lensing signal clearly separates from the visible glowing gas after a collision. Exactly what you'd expect if an invisible substance had passed straight through relatively undisturbed, while ordinary gas collided and slowed down, has increasingly weighed against it. The standard dark matter picture remains the position held by the overwhelming majority of the field, but it's honest to note the debate hasn't been unanimous. Dark matter, in other words, pulls things together. It adds gravity, holding galaxies and galaxy clusters intact that would otherwise fly apart. Dark energy does the opposite. It pushes things apart, a repulsive effect spread uniformly through space itself, responsible for the accelerating expansion this entire video is about. According to the standard model built from Planck satellite data, the universe breaks down into roughly 68% dark energy, 27% dark matter, and just 5% ordinary matter, the atoms that make up every star, every planet, and everyone who has ever lived. Every person, every galaxy, every photon of starlight ever observed by any telescope in human history, all of it, together, accounts for only about 1/20th of everything that exists. And even within that small 5% slice, there's a second, lesser-known puzzle worth a passing mention. For years, direct surveys of stars, gas, and galaxies only ever managed to actually locate a portion of the ordinary matter theory said should be out there, with a meaningful fraction seemingly missing even from the small sliver we're supposedly made of. Later observations have since tracked down much of that missing ordinary matter, hiding in thin, hard-to-detect gas strung out between galaxies, sometimes called the warm-hot intergalactic medium, gas spread so thin and heated to such extreme temperatures by the gravitational churn of large-scale structure that it barely emits enough light to be seen by any instrument, a reminder that even the boring, everyday 5% of the universe took real work to fully account for. There's a wrinkle to this story that took nearly a century to fully surface. When Lemaitre's 1927 paper was finally translated into English in 1931, for publication in the monthly notices of the Royal Astronomical Society, the translation quietly dropped the section where he had calculated his own value for the expansion rate, the section that would have given him a much stronger claim to priority over Hubble. For decades, historians assumed this was simply an editorial trim, unremarkable and probably harmless. Then, starting around 2011, a Canadian astronomer named Sidney Vandenberg revisited the translation history and flagged the missing section publicly, and the resulting debate over who really deserved credit for discovering cosmic expansion escalated fast, eventually spilling into the pages of the journal Nature itself, with astrophysicist Mario Livio publicly calling for the historical record to finally be set straight. Livio eventually tracked down enough evidence, including letters in Lemaitre's own hand, to conclude the priest had translated the paper himself and had deliberately chosen to leave that section out, apparently because he considered the value outdated by the time of the English publication and preferred to simply point readers toward Hubble's more recent, more precise results instead. Livio's research into Lemaitre's private correspondence painted a picture of a scientist who seemed almost entirely unbothered by the whole question of credit, more interested in the physics being right than in his own name being attached to it. 5 years after that, in 1927, a Belgian physicist and Catholic priest named Georges Lemaitre, trained at Cambridge, Harvard, and MIT, independently arrived at the same basic conclusion. Lemaitre combined redshift data, mostly built on Slipher's earlier measurements, with distance estimates, and derived a linear relationship between how far away a galaxy sits and how fast it appears to recede. He even calculated a version of what we'd now call the Hubble constant, landing on values around 575 to 670 kilometers per second per megaparsec, depending on how he grouped his data. There was just one problem. Lemaitre published his paper in French, in a relatively obscure Belgian journal, and almost nobody outside a small circle of specialists noticed. 2 years later, in 1929, Edwin Hubble published his own version of essentially the same discovery. Hubble's own path to that moment had already taken a strange enough route on its own. A tall, athletic student at the University of Chicago, good enough at boxing that a promoter reportedly wanted to train him to fight for a world title, Hubble won a Rhodes Scholarship to Oxford in 1910, where, at his father's insistence, he studied law rather than science, passed the bar exam back in the United States, and spent a year practicing as an attorney in Kentucky before deciding he was bored and returning to the University of Chicago to finally pursue the astronomy career he'd apparently wanted all along, interrupted again by service in the infantry during the First World War, before he finally arrived at Mount Wilson Observatory in California in 1919. Working there a decade later, he published his velocity-distance relationship, using distances he had calculated and redshift measurements that, once again, leaned heavily on Slipher's earlier work. The assistant who helped him gather that data has one of the more unlikely career paths in the history of astronomy. Milton Humason had dropped out of school as a teenager, taken a job driving mule trains hauling lumber and equipment up the mountain during Mount Wilson Observatory's construction, and later worked there as a janitor, with no high school diploma to his name. His technical skill behind the telescope caught the observatory director's attention, and by 1919 he'd been promoted onto the professional scientific staff itself, an almost unheard-of leap at the time. Hubble recruited him in 1928 specifically to help record redshifts for even more distant nebulae, pushing the dataset further out than anyone had managed before, and Humason went on to personally measure the velocities of hundreds of galaxies over the following decades, becoming one of the most respected observers of his generation, despite never once setting foot in a university classroom. Hubble's paper landed with far more visibility than Lemaitre's had. It was in English. It came out of a well-known American observatory, and it stuck. The relationship between distance and recession velocity became known simply as Hubble's law, and the man's name became permanently attached to the discovery of cosmic expansion. What makes this genuinely interesting is how little Lemaitre seemed to care about getting credit. Science historian Mario Livio, who studied Lemaitre's own letters, found that the priest was, in his words, not at all obsessed with establishing priority for his original discovery. And since Hubble's results were already out in the world by 1929, Lemaitre apparently saw no reason to go back and republish his own earlier, more tentative findings just to stake his claim. It took until 2018 for the record to get formally corrected, when the International Astronomical Union voted to officially rename the relationship the Hubble-Lemaitre law, giving both men their place in the name that describes the discovery. And here's a detail that tends to get left out of the popular version of this story entirely. Hubble's own original number was wildly off. His 1929 estimate for the expansion rate came out to roughly 500 kilometers per second per megaparsec, somewhere around 7 times higher than the value astronomers accept today. The error traces back to bad distance measurements available at the time. Hubble had calculated the distance to the Andromeda galaxy at around 1 million light-years, when it actually sits closer to 2.5 million light-years away. Fix the distances, and the expansion rate comes down dramatically. It would take decades of refinement, better telescopes, better standard candles, and eventually entirely new categories of instruments before anyone got a number close to what's accepted now. Before Penzias and Wilson stumbled onto their discovery, it's worth knowing that the whole idea of a universe with a definite beginning wasn't universally accepted, not even among professional cosmologists, well into the mid-20th century. A rival framework called the steady-state theory, developed by the British astronomer Fred Hoyle, together with Hermann Bondi and Thomas Gold, three colleagues who had worked together on radar research during the Second World War, proposed something genuinely different: that the universe had no beginning and no end at all, that it had always looked roughly the way it looks now, and that as it expanded, new matter was continuously created out of the vacuum of space itself to keep its overall density constant, forever, stretching backward and forward in time without limit. The idea's origin story, as the three men themselves later told it, has nothing to do with equations at all. In 1946, the three friends went to see a British horror film called Dead of Night, an anthology built around a circular, looping plot where the final scene folds back into the first, leaving the story with no true beginning and no true end. Walking back to Bondi's rooms at Trinity College afterward, glasses of rum in hand, Gold reportedly turned to the others and asked, simply, "What if the universe is like that?" That offhand question, sparked by a horror movie rather than a telescope, became the seed of an entire cosmological model, one that would go on to seriously compete with the Big Bang for the better part of 2 decades. Hoyle went further than his two colleagues, proposing an actual physical mechanism for the theory's continuous creation of matter, something he called the C field, standing for creation, a field with negative pressure that could drive expansion while simultaneously seeding new matter into existence, a concept that, in hindsight, shares an odd mathematical family resemblance to both the inflaton field described earlier and the dark energy that would eventually replace the steady-state theory altogether. Here's a detail that tends to get told wrong, repeated so often that the incorrect version has practically become the accepted story. During a BBC radio broadcast on March 28, 1949, Hoyle, arguing for his steady-state model, described the rival theory as the hypothesis that all matter in the universe was created in one Big Bang at a particular time in the remote past. That phrase, Big Bang, is exactly where the name of the theory this entire video is built on actually comes from, coined not by one of its supporters, but by one of its fiercest critics. Popular retellings often claim Hoyle meant the phrase as an insult, a dismissive jab at a theory he thought was scientifically unsound. More careful historical research, including work by the science historian Helga Krag, along with Hoyle's own later explanation given decades afterward, suggests that isn't quite right. Hoyle himself said he was simply straining, on live radio, with no visual aids and nothing but his own voice, to find a vivid, memorable image for a general audience. Whatever his intent, the name stuck, slowly at first, only really catching on in wide use by the 1970s. Long after the steady-state theory it was coined to criticize had already lost the argument. And it lost that argument specifically because of what Penzias and Wilson were about to accidentally discover. The steady-state theory made a clean, testable prediction. If the universe truly had no beginning, there should be no leftover radiation from any single, primordial hot moment, because there never was one. The cosmic microwave background, once identified, was exactly that kind of leftover radiation, direct, physical evidence of a hot, dense early state the steady-state model said could never have existed. Its discovery didn't just support the Big Bang model, it functioned as close to a decisive blow against its chief rival as cosmology has ever produced. Even Hermann Bondi, one of the steady-state theory's own co-creators, had already shown signs of doubt years earlier, writing in 1952 that Lemaitre's expanding model seemed to be the best relativistic cosmology could offer, a striking admission from a man who spent much of his career defending the opposite position. The next piece of this puzzle fell into place almost by accident, in 1964 and 1965, at Bell Labs in Holmdel, New Jersey. Two radio astronomers, Arno Penzias and Robert Wilson, were working with a large horn antenna that had originally been built for satellite communication, and they kept picking up a strange, faint, persistent hum of noise that seemed to come from every direction in the sky, all the time, no matter where they pointed the instrument. They assumed it was a flaw in their equipment. They checked for interference from nearby New York City. They cleaned the antenna. At one point, they even removed a pair of pigeons that had taken up residence inside the horn, along with what one account politely calls their accumulated droppings, thinking that might be the source of the interference. None of it worked. The noise stayed exactly the same, day or night, every season of the year. What Penzias and Wilson didn't know at the time was that just up the road, at Princeton University, a team led by physicist Robert Dicke was actively predicting that exactly this kind of signal should exist, a faint leftover radiation from the earliest, hottest moment of the universe's history, stretched by billions of years of cosmic expansion into microwave wavelengths. When the two groups connected, the picture clicked into place. Penzias and Wilson hadn't found a flaw in their antenna. They had found the afterglow of the Big Bang itself, now known as the cosmic microwave background, or CMB, the oldest light that exists, released when the universe was only about 380,000 years old, once it had finally cooled enough for atoms to form and light to travel freely for the first time. Penzias and Wilson won the Nobel Prize in Physics in 1978 for a discovery they had essentially stumbled into while trying to get rid of what they thought was static. The CMB turned out to be one of the single most useful tools cosmology has ever had, because it works like a baby picture of the entire universe, a snapshot of what everything looked like in its infancy, encoded in the tiny temperature variations scattered across that ancient light. NASA's COBE satellite, launched in 1989, was the first instrument sensitive enough to detect those tiny variations, known as anisotropies, and two of its lead scientists, John Mather and George Smoot, picked up their own Nobel Prize in 2006 for the achievement. When Smoot announced the discovery at a packed press conference in April of 1992, he reached for language that went well beyond ordinary scientific caution, telling the room, "If you're religious, it's like seeing God," a line that followed him for the rest of his career, and one he spent years afterward carefully explaining he'd meant only as a metaphor, not a literal claim. Stephen Hawking, for his part, called the COBE results the greatest discovery of the century, if not of all time. Part of what made COBE's results so powerful was that the CMB matched, almost perfectly, the theoretical shape of what physicists call black body radiation, the smooth curve of light a perfectly efficient absorber and emitter would produce at a given temperature. That near-perfect match was itself a stunning confirmation of the Big Bang picture, because it's exactly what you'd expect from the leftover glow of an incredibly hot, incredibly dense early universe cooling smoothly as it expanded, now measured at a temperature of roughly 2.7 degrees above absolute zero. Then came NASA's WMAP satellite in 2001, pushing the precision further, and finally, in 2009, the European Space Agency launched Planck, named after the physicist Max Planck, whose work on blackbody radiation over a century earlier turned out to be exactly the physics needed to eventually decode the CMB's own signal. Planck's map captured that ancient light as it existed when the universe was just 380,000 years old, back when it was still an unimaginably hot, dense soup of protons, electrons, and photons colliding constantly at a temperature around 2700 degrees Celsius. Once things cooled enough for those protons and electrons to combine into neutral hydrogen atoms, a transition physicists call recombination, photons stopped constantly scattering off charged particles and were, essentially, set free to travel in straight lines across the universe for the first time, and those exact photons, stretched by billions of years of expansion, are the ones Planck spent years mapping in extraordinary detail. When Planck's first full results came out in 2013, they didn't just confirm the Big Bang model in broad strokes, they pinned down specific numbers with startling precision. The age of the universe came out to 13.82 billion years. It's worth knowing that this number isn't resting on the CMB alone. Astronomers have an entirely separate, independent cross-check available: the ages of the oldest stars ever found, particularly in dense clusters called globular clusters, calculated using well-established models of how stars burn through their fuel over time. Whatever age you calculate for the universe, it has to come out older than the oldest stars inside it, or the whole model has an obvious contradiction on its hands: stars older than the universe that supposedly made them. Estimates for the oldest globular clusters, places like the one called Messier 4, generally land somewhere in the range of 12 to 13 billion years, allowing enough breathing room below Planck's 13.82 billion year figure for those ancient stars to have formed, evolved, and aged into the state we observe them in today, without the timeline ever running impossibly tight. The oldest globular cluster stars come out consistently a bit younger than Planck's number, exactly the relationship the model requires. Two completely independent methods, one based on the leftover light from the Big Bang, and one based on nuclear physics inside ancient stars, agreeing with each other. And buried inside that same CMB dataset was a value for the Hubble constant, the same number Hubble himself had tried to measure back in 1929, except this time it was being extracted from the oldest light in existence rather than from nearby galaxies. Planck's number came out to 67.37 kilometers per second per megaparsec, give or take about half a kilometer per second. That number would turn out to matter enormously, because it was about to collide, hard, with a completely different measurement coming from an entirely different direction. Before we get to that collision, there's a piece of theory that has to slot in here, because without it, the whole picture of the early universe has an obvious hole in it. Planck's map of the CMB showed the early universe to be remarkably smooth and remarkably flat, uniform in temperature to an almost absurd degree in every direction we look, varying by only a few parts in 100,000 from one patch of sky to another, tiny ripples riding on top of an otherwise nearly featureless glow. And that smoothness is actually a problem, not a comfort, because under a plain, unmodified Big Bang model, regions of the sky on opposite sides of us should never have had time to reach the same temperature as each other. Light, and therefore any influence at all, hasn't had enough time since the Big Bang to travel between those regions and let them equalize, which means, by the simplest version of the theory, they shouldn't match. But they do match, almost perfectly. This is called the horizon problem, and there's a companion issue called the flatness problem, the fact that the universe's overall geometry sits so close to perfectly flat that the range of starting conditions which could have produced that flatness is almost impossibly narrow, like balancing a pencil on its tip and having it stay there for 14 billion years. Cosmologists describe this with a number called omega, representing the universe's actual density divided by the exact density that would produce a perfectly flat geometry. Push omega even slightly above 1 in the early universe, and the whole cosmos should have collapsed back on itself long ago. Push it even slightly below 1, and everything should have flown apart into an empty, matter-starved void almost immediately. Measurements consistently put omega within a hair's breadth of exactly 1, and getting a number that precise out of essentially random initial conditions, without something like inflation actively smoothing and flattening the geometry in the first fraction of a second, looks less like good luck and more like a genuine puzzle needing an explanation. It's one of the clearer examples in all of cosmology of a strange coincidence eventually turning into a real scientific clue, the kind of oddly specific number that keeps nagging at physicists until somebody finally works out the mechanism behind it. In December of 1979, a young particle physicist named Alan Guth had what he later described as a spectacular realization while working through exactly this kind of puzzle, motivated originally by a completely different question about why we don't see certain exotic particles called magnetic monopoles in nature today. Guth worked out that if the very early universe passed through an incredibly brief period of exponential expansion, ballooning outward by an enormous factor in a fraction of a second, both the horizon problem and the flatness problem would resolve themselves automatically. The engine behind this proposed burst of growth is a hypothetical field physicists call the inflaton, a form of energy that, under the right conditions, generates a kind of gravity that pushes rather than pulls, exactly the repulsive behavior needed to blow space apart so violently in such a short window of time, before the field itself decayed and released its energy as the hot, dense soup that would go on to become the ordinary Big Bang. Regions that look impossibly similar today would actually have been in close contact before that explosive growth stretched them apart, smoothing everything out first and then blowing it up to cosmic scale. Guth published the idea formally in January of 1981 in a paper that has since been cited something like 13,000 times, and he gave this brief, explosive early growth spurt a name: inflation. Other physicists quickly built on the idea. The Soviet physicist Andrei Linde and, separately, the team of Andreas Albrecht and Paul Steinhardt refined and extended Guth's original version within about a year, fixing technical problems with how the initial theory predicted inflation would end. Data from later missions, WMAP in the 2000s and Planck after it, ended up matching inflation's predictions for the specific pattern of tiny density fluctuations seeded in the early universe with striking precision, and that agreement is a big part of why inflation, while still technically a theoretical model rather than something observed directly, is now the leading explanation among cosmologists for why the universe looks the way it does at the very largest scales. Here's where things get genuinely strange, and where it's worth being careful about the line between well-tested physics and speculation that sounds like physics. In December of 1981, Guth came across a paper by Linde exploring what would happen if inflation didn't stop everywhere at once, uniformly, the way the simplest version of the theory assumed. Linde's idea, developed further over the following years into what's now called eternal inflation, suggests that inflation might never actually stop completely across the whole of existence. In any given patch of space, inflation can end, and when it does, that patch settles down into an ordinary, slowly expanding universe, like our own, essentially its own miniature Big Bang. But in the space between those patches, inflation just keeps going, forever, endlessly spawning new patches, new bubble universes, over and over, without end. Under some versions of this framework, each of those separate bubble universes could, in principle, end up with different physical constants, different laws of physics, maybe even different numbers of spatial dimensions, entirely walled off from one another by the never-ending inflation still happening in between. Some theorists working in string theory have gone further still, describing an almost incomprehensibly large landscape of mathematically possible universes, each with its own combination of physical constants, with eternal inflation acting as the mechanism that could, in principle, actually bring each one of those mathematical possibilities into physical existence somewhere within an ever-growing multiverse. It's an idea that sounds more like science fiction than science, and the honest answer is that right now, nobody can definitively say which category it belongs in. Guth himself, decades later, described the basic mechanism behind the idea in strikingly simple terms. Once inflation starts, he said, it never stops completely. In a region where it does stop, space and time settle gently into a universe like our own, while everywhere else, space keeps expanding exponentially, bubbling forever, each disconnected bubble growing under its own separate initial conditions. Andre Linde himself has been careful about how far to push this. In his own words, the multiverse hypothesis is a very attractive idea, but it is still a hypothesis, and it needs to be tested. That caution matters, because right now, there is no confirmed way to test it. Eternal inflation and the multiverse it implies are taken seriously by many theoretical physicists, and they follow logically from mathematics that has otherwise proven itself useful, but as of today, they make essentially no predictions that can be independently checked against observation, and there is no direct evidence for any universe beyond our own. It belongs firmly in the category of serious, mathematically motivated speculation, genuinely worth knowing about, but genuinely different in kind from the CMB, from Hubble's law, from the 1998 supernova discovery, all of which rest on data anyone can go check for themselves. With that distinction clearly drawn, let's get back to what we can actually measure. But before we get to that collision, there's another discovery that has to come first, because it completely rewrote what scientists thought the expansion of the universe was even doing. Through the 1990s, two rival teams of astronomers were racing to measure the same basic quantity, using a class of exploding stars called Type 1a supernovae, as what astronomers call standard candles, objects with a known, predictable brightness that let you calculate distance based on how dim they appear from Earth. The naming itself is just an older astronomical classification system, based on which chemical signatures show up in a supernova's light, and Type Ia specifically means the explosion shows no hydrogen at all in its spectrum, a telltale sign of exactly this kind of white dwarf detonation rather than the collapse of a massive young star. A Type Ia supernova happens when a dead star called a white dwarf pulls in enough material, usually from a companion star, to cross a specific mass threshold, worked out mathematically by the Indian-American astrophysicist Subrahmanyan Chandrasekhar, and now named the Chandrasekhar limit in his honor, sitting at roughly 1.4 times the mass of our own Sun, at which point it detonates in a runaway thermonuclear explosion. Chandrasekhar worked out this limit as a young man in his early 20s, sailing from India to England in 1930, and it would eventually earn him his own Nobel Prize in Physics decades later, in 1983, for entirely different but related work on the physics of dying stars. Because that threshold is essentially the same everywhere in the universe, these explosions all release roughly the same amount of energy, which means they all appear with roughly the same intrinsic brightness. Find one, measure how bright it looks from Earth, compare that to how bright it should be intrinsically, and the difference tells you the distance, the same basic logic as knowing a light bulb's true wattage and then judging distance purely by how dim it looks from across a field at night. Perlmutter co-founded the Supernova Cosmology project back in 1988, spending nearly a decade building up the methods and the international collaboration needed to hunt for these exploding stars across enormous cosmic distances, pulling in researchers from the United States, France, Sweden, the United Kingdom, Chile, Japan, and Spain, among other countries, all coordinated out of Lawrence Berkeley National Laboratory and the University of California, Berkeley, where Perlmutter held his academic post. Schmidt formed his rival team, the High Z Supernova Search Team, in 1994, based at the Australian National University, using broadly similar methods, with Adam Rees, then a young postdoctoral researcher, leading the actual analysis of that team's data. The two groups spent the mid to late 1990s essentially racing each other toward the same finish line, unaware, at least initially, that they were both about to stumble into the same shocking result. Both teams were chasing the same goal, and it wasn't what you might expect. Gravity pulls things together, so both teams assumed the expansion of the universe, driven outward by the Big Bang, should be gradually slowing down over time as all that matter's gravity tugged against it. The entire point of studying these distant, ancient supernovae was to measure exactly how much that slowdown was happening. If the universe really were decelerating, distant supernovae should have appeared slightly brighter than a simple, coasting expansion would predict. Because in a decelerating universe, light from the deep past would have less distance to cross to reach us than it would in a universe expanding at a constant rate. That was the expected signature both teams were hunting for. Instead, both teams found something that made no sense within the framework anyone was using. The distant supernovae were dimmer than a coasting universe would predict, not brighter. Dimmer means farther away than expected, and farther away than expected, given how much time had passed, meant only one thing: the expansion of the universe was not slowing down. It was speeding up. Saul Perlmutter later described the moment plainly, saying his first reaction was the reaction of any physicist in that kind of situation, wondering which part of the analysis needed a new calibration, assuming somewhere in the chain of measurements something had gone wrong. It hadn't. During a colloquium Perlmutter gave in November of 1997, presenting the early hints of this result, the cosmologist Joel Primack reportedly stood up, and rather than addressing Perlmutter directly, turned to the rest of the audience and said, "You may not realize this, but this is a very big problem." He was right. Perlmutter would later reflect that the scientific community's acceptance of this surprising result happened almost unbelievably fast, calling it maybe the fastest acceptance of a big surprise in the history of science. Both teams published their findings within roughly a year of each other, the High Z team's 10 supernovae appearing in the Astronomical Journal in 1998, and Perlmutter's larger sample of 42 supernovae following in the Astrophysical Journal in 1999. The two independent, competing groups had landed on the same impossible conclusion using different data. The journal Science named it the breakthrough of the year for 1998. The explanation that emerged to account for the acceleration was something scientists started calling dark energy, a mysterious, repulsive force or energy pushing space apart, uniformly, everywhere, at every point in the cosmos, and by most current estimates, making up somewhere around 2/3 to 3/4 of everything that exists in the universe. Nobody, then or now, actually knows what dark energy is. It remains, more than a quarter century later, a name for an effect rather than an explanation for a cause. A smaller group of theorists has spent those same decades pursuing a different kind of answer entirely, exploring whether the acceleration might not require any new substance at all, but instead reveal that gravity itself, Einstein's general relativity, needs a small correction at the very largest cosmic scales, an approach broadly known as modified gravity. These models remain a minority position, harder to reconcile with certain other observations than the standard dark energy picture, but they're a reminder that even the existence of dark energy as a distinct substance, not just its behavior, isn't entirely beyond question. The scientific establishment eventually caught up with just how significant this had been. In 2011, Perlmutter, Schmidt, and Rees were jointly awarded the Nobel Prize in Physics for the discovery of the accelerating expansion of the universe through observations of distant supernovae, as the official citation put it. Perlmutter received half the prize money, worth roughly 10 million Swedish kroner in total, or about $1.4 million at the time, with Schmidt and Rees splitting the other half between them. There's a small, telling detail buried in the middle of this rivalry too, worth pausing on. An astronomer named Alex Filippenko, based at UC Berkeley, was at different points in the 1990s a member of both competing teams, the Supernova Cosmology Project and the High Z Supernova Search Team, watching essentially the same impossible result take shape from two different vantage points inside the same scientific race. All three laureates traveled to Stockholm that December to receive their medals from the King of Sweden, the traditional ceremony every Nobel Prize in Physics has followed since the award's founding in 1901. A strange kind of full circle for two rival teams who had spent years racing each other toward the same discovery, only to end up sharing the same stage. When he learned he'd won, Perlmutter said simply that he was delighted, excited, and deeply honored. What had started as an attempt to measure how fast gravity was pulling the cosmos back together had ended with proof that something far stranger was pushing it apart, faster and faster, with no sign of stopping. Which brings us back to that collision we mentioned earlier, the one between Planck's number and everybody else's. Remember, Planck's CMB-based measurement of the Hubble constant came out to 67.37 kilometers per second per megaparsec, drawn from the oldest light in the universe. But there is a second, completely independent way to measure the exact same number, using what astronomers call the distance ladder, a chain of measurements built on Cepheid variable stars, whose brightness pulses in a way that reveals their true distance, combined with those same Type 1a supernovae used in the 1998 discovery. This is a local universe measurement, built from galaxies relatively close to us, rather than light from the dawn of time. The team most associated with this method is called SH0ES, short for supernovae, and H0 for the equation of state, and it's led by none other than Adam Rees, the same scientist who led the analysis behind the original 1998 acceleration discovery, now at Johns Hopkins University and the Space Telescope Science Institute in Baltimore, spending the years since his Nobel Prize trying to pin down the very number his own earlier work helped establish was accelerating in the first place. Their results, refined again and again over the years, keep landing in a completely different place than Planck's. One widely cited SH0ES value comes in at 73.04 kilometers per second per megaparsec. Other analyses from the same general approach have landed at 73.52 and at 74.03. These aren't small, sloppy studies. These are extremely careful, heavily scrutinized measurements, and they keep refusing to agree with the CMB-based number, no matter how much precision gets thrown at either side. Here's what makes this genuinely strange, rather than just a rounding error. As both measurement techniques have gotten more precise over the decades, the gap between them hasn't closed. It's gotten more statistically solid. Researchers have now produced more than 1,000 separate estimates of the Hubble constant over roughly 60 years of trying, and today, the local universe value and the early universe value are both pinned down with real confidence. They just don't match each other. Some analyses put the disagreement at around 4.1 standard deviations. Others push it as high as 5. It's worth knowing what that number, physicists usually call it sigma, actually represents, since it comes up throughout this video. Sigma measures how likely it is that a gap this size could show up purely by random chance or measurement noise, even if the two things being compared were secretly identical. A gap of 1 or 2 sigma happens by chance fairly often, nothing to get excited about. A gap of 5 sigma, the traditional bar physicists set for officially declaring a discovery, corresponds to roughly a 1 in a few million chance of being a random fluke. A 4 to 5 sigma Hubble tension is not a coin flip. It's the kind of statistical gap that gets scientists' full attention. This mismatch earned its own name, the Hubble tension. Nobody has a confirmed explanation for it. A handful of possibilities are on the table. Maybe there's a hidden systematic error somewhere in how Cepheid stars get calibrated for brightness. Maybe there's an issue with how the CMB's own directional patterns, something called the CMB dipole, get accounted for in the Planck analysis. The most cautious explanation is that there's simply an unknown flaw sitting somewhere in one of the two methods. But even that turns out to be an uncomfortable answer, because it would require multiple unrelated mistakes to explain the full size of the gap, and nobody has found a single convincing candidate for what that mistake actually is. The less cautious, more exciting possibility on the table is that there's no mistake at all, and that the universe itself is telling us our standard model of cosmology, the one physicists have leaned on for decades, is missing something. What's genuinely striking about the Hubble tension is that it isn't just two lonely numbers arguing with each other. Over the years, astronomers have thrown an entire toolbox of independent techniques at this problem, hoping one of them would break the tie, and instead, the results have mostly clustered into the same two feuding camps. The Pantheon Plus dataset, combining supernova measurements with the SH0ES approach, landed at 73.4 km per second per megaparsec. A study using Type II supernovae as a different kind of standardizable candle came in even higher, at 75.4. Researchers using something called the Tully-Fisher relation, discovered in the 1970s, which connects how fast a spiral galaxy rotates to how intrinsically bright it is, the same basic logic once again. A faster spinning galaxy generally contains more mass and therefore shines more brightly, letting you infer true brightness from rotation speed alone and calculate distance the usual way, have consistently found values above 73 as well, reinforcing that this tension isn't tied to any single distance indicator or any single team's methodology. Then there are the techniques that lean toward the lower, Planck-like end of the range. A study using the statistics of cosmic voids, essentially mapping the empty regions between galaxy clusters and tracking how their sizes and shapes evolve as space expands around them, produced a value of 67.3. Measurements using the cosmic microwave background power spectrum from a ground-based instrument in Antarctica called SPT-3G returned 68.3. One of the more remarkable entries on this list traces back to a single night, August 17, 2017, when the advanced LIGO and Virgo gravitational wave detectors picked up ripples in the fabric of space-time itself, the signature of two neutron stars spiraling into each other and merging, roughly 130 million light-years away. Less than 2 seconds later, NASA's Fermi satellite detected a burst of gamma rays from the same patch of sky, and within hours, telescopes around the world had zeroed in on a fading point of light in a galaxy called NGC 4993, the glowing afterglow of the collision itself, an event astronomers call a kilonova. It was the first time in history anyone had detected the same cosmic event in both gravitational waves and light, a moment now generally regarded as the birth of what's called multi-messenger astronomy. Because the gravitational wave signal itself directly encodes the distance to the merger, no calibration ladder required, scientists realized they could use events like this one as what's called a standard siren, the gravitational wave equivalent of a standard candle, an entirely independent way to measure the Hubble constant using nothing but the shape of the space-time ripple itself, paired with the galaxy's known recession velocity. That first measurement, back in 2017, landed close to 70, roughly splitting the difference between the two feuding camps. Though with wide enough uncertainty at the time, that it couldn't settle anything. The more refined 2023 version of this kilonova technique, revisiting the same event's expanding fireball years later, came out closer to 67, landing squarely on the CMB side of the divide. Even planetary nebulae, using archival data from the Very Large Telescope across 16 galaxies, have produced values in between, around 74.2, with wide enough uncertainty that the result doesn't cleanly resolve anything either way. Look across that entire spread of independent techniques, built by different teams, using entirely different physics, different instruments, and different assumptions, and a pattern holds firm. Nearly everything anchored in the nearby, local universe, Cepheids, supernovae, Type II supernovae, the Tully-Fisher relation, planetary nebulae, gravitational wave sirens measured close to home, keeps landing up around 73 to 75. Nearly everything anchored in the early universe, the cosmic microwave background, cosmic voids, the more distant kilonova remeasurement, keeps landing down around 67 to 68. It is not one flawed study against the world. It is dozens of careful, independent measurements, sorting themselves into exactly two camps, refusing to blend into a single consensus number, no matter how the data gets sliced. That consistency is exactly why so many cosmologists have stopped assuming this is simply a matter of somebody, somewhere, making an error, and started taking seriously the idea that the standard model of the universe itself might be missing a piece. Before we get to the most recent chapter of the Hubble tension itself, there's a related mystery worth folding in here, because it comes from a completely different instrument and a completely different kind of measurement, yet it's rattling the same standard model of cosmology from another angle entirely. Since 2022, the James Webb Space Telescope has been peering back toward the very edge of observable time, catching light from galaxies as they looked just a few 100 million years after the Big Bang, and what it's been finding doesn't fit comfortably into the standard picture. The telescope itself is built specifically for this kind of hunt, parked about 1 million miles from Earth at a gravitationally stable point called L2, carrying a primary mirror 6.5 meters across, made of 18 gold-coated hexagonal segments, and tuned to detect infrared light specifically because, as we covered earlier, the most ancient light in the universe has been redshifted well out of the visible range by the time it reaches us. These early galaxies keep showing up too big, too bright, and too mature for how young the universe was when their light left them. One widely discussed 2023 study found candidate galaxies so massive, given their inferred age, that Penn State astronomer Joel Leavitt described them as being in tension with 99% of models for cosmology, adding that accounting for that much mass would require either revising the models of cosmology itself or revising the entire understanding of how galaxies grow from small clumps of gas and dust into the massive structures we see today. One particular galaxy, catalogued as GNZ11, gets its name from exactly the kind of redshift measurement this whole video has been built around. That Z11 at the end of its name is shorthand for a redshift value of about 11, meaning the light from that galaxy has been stretched so dramatically by cosmic expansion that its wavelength is now roughly 12 times longer than when it was originally emitted. Astronomers use this Z number as their standard shorthand for both distance and cosmic age at once, since a specific redshift corresponds to a specific moment in the universe's expansion history. Confirmed through detailed JAST spectroscopy, GNZ11 is being observed as it existed just 430 million years after the Big Bang, and researchers described it outright as a remarkable galaxy with extreme properties. Another study identified a galaxy that had already stopped forming new stars entirely, gone quiet, just 700 million years into the universe's 14 billion-year history, essentially a retired galaxy showing up impossibly early in cosmic time. To be clear, this isn't the same puzzle as the Hubble tension we just walked through. It's a related, but genuinely separate open question, this one about how quickly galaxies were able to grow large, rather than about the expansion rate itself. Some researchers have proposed theoretical models involving a concept called early dark energy that might resolve both puzzles simultaneously with a single underlying fix. The basic idea is that dark energy might not have been negligible only in the very distant past and dominant only today, the assumption baked into the standard model, but might have had a brief, extra surge of influence sometime in the universe's infancy before settling back down. A temporary boost like that, early on, could in principle both nudge the Hubble constant toward reconciling its two feuding values and give gravity a small additional early assist in growing galaxies faster than the plain model predicts. It's an elegant idea, precisely because it tries to kill two separate birds with one theoretical stone, but that elegance doesn't make it correct, and it remains speculative and unconfirmed. And it's worth being fair to the data here too. Follow-up studies have since found that some of the most extreme mass estimates get pulled back down once astronomers account for contamination from actively feeding black holes and the inherent uncertainty in how stellar mass gets estimated from just images in the first place. Still, even after those corrections, most researchers agree the number of large, mature galaxies this early in cosmic history remains higher than the standard model predicted. One more thread in a growing pile of evidence suggesting our working picture of the universe's early years needs at least some kind of update. Since 2022, JUICE has also turned up an entirely separate category of oddity: hundreds of tiny, extremely compact, unusually red objects that astronomers, only half joking, started calling little red dots, first flagged in the telescope's very earliest deep-field images and confirmed as a genuinely new class of object across dozens of follow-up surveys over the following 2 years. They showed up in large numbers within the universe's first billion years, and then largely vanished from view again before the universe reached about 2 billion years old, which is itself strange. An entire population of objects with a beginning and an apparent ending packed into a narrow slice of cosmic history. At first, researchers assumed they might simply be compact, mature galaxies, but the telescope couldn't resolve them into any recognizable galactic shape, meaning whatever they were had to be almost absurdly small and dense, in some cases estimated at over 250 billion times the brightness of our Sun, crammed into a region smaller than a third of a light-year across. Caitlin Casey, an astronomer at the University of Texas at Austin, described the basic puzzle plainly. It was a mystery as to why they were so spatially compact. The explanation gaining the most traction recently treats these objects as something genuinely new, sometimes nicknamed black hole stars, colossal, glowing balls of hot gas larger than an entire solar system, powered not by nuclear fusion the way ordinary stars are, but by a supermassive black hole feeding at their core, wrapped in a dense cocoon of ionized gas. Princeton astrophysicist Jenny Green, discussing the emerging picture, said simply, "I think we're closing in on an answer. One proposed explanation for their eventual disappearance is that these black hole stars burn through an intense, short-lived growth spurt, powering themselves brightly for a while, before the growing black hole at their center eventually clears away the dense gas cocoon feeding it, extinguishing the very light that made them visible in the first place, essentially outgrowing the disguise that let astronomers spot them in the first place. If that explanation holds, these objects may represent a genuine missing link in how the very first supermassive black holes managed to grow so large, so fast, in such a short amount of time, in a universe that had barely had any time at all to build them. The nickname itself started as an informal shorthand among researchers passing images back and forth, half joking about how strange it was that JUICE kept flagging these tiny, unremarkable-looking red smudges as some of the most confounding objects it had ever photographed, and the name simply stuck once papers started using it in earnest. It's a reminder that even while cosmologists argue over the expansion rate and the fate of everything, JUICE keeps turning up entirely new categories of object that nobody had a name for 3 years ago. In a strange way, JUICE and DESI are working the same underlying mystery from opposite ends of the timeline. JUICE staring as far back as light will allow to catch the universe still assembling itself, while DESI maps the more recent 11 billion years to catch dark energy's fingerprints on everything built since. Neither instrument was designed with the other's puzzle in mind, and yet both keep turning up evidence that the tidy, decades-old standard model of cosmology may have holes in it nobody had previously been equipped to see or even ask about. That brings us to the most recent chapter in this story, and it's still being written. Since 2021, An instrument called DESI, the Dark Energy Spectroscopic Instrument, mounted on the Mayall telescope in Arizona, has been building the largest three-dimensional map of the universe ever constructed, using the positions of some 15 million galaxies, and growing, along with quasars, the extraordinarily bright, distant cores of galaxies powered by feeding supermassive black holes, visible across even greater distances than ordinary galaxies, and useful for tracing the cosmic web out to the very edges of DESI's reach, to track how dark energy has behaved across roughly the last 11 billion years of cosmic history. DESI works by simultaneously capturing the spectrum of light from thousands of individual targets at once, using an array of 5,000 tiny robotic positioners, each roughly the size of a pencil, mounted across the telescope's focal plane. Each one holding a hair-thin optical fiber and swiveling independently to line up with a single pre-selected galaxy, precisely aimed at a specific target in the sky to within a tolerance described as roughly a tenth the width of a human hair, all 5,000 repositioning themselves in perfect coordination between exposures, night after night. From that flood of spectra, researchers measure something called baryon acoustic oscillations, faint ripples frozen into the large-scale distribution of galaxies, essentially fossilized sound waves left over from the early universe, before atoms had even formed, when the hot plasma of the cosmos was still sloshing back and forth. Here's why those frozen ripples are so useful. Before the universe cooled enough for neutral atoms to form, ordinary matter and light were still tightly coupled together, and sound waves, real pressure waves, rippled outward through that hot plasma exactly the way sound ripples outward through air. Those waves traveled for a fixed, calculable amount of time before the plasma cooled and light finally broke free, at which point the waves froze in place, imprinted permanently into the pattern of where matter would later clump together to form galaxies. Because physicists can calculate exactly how far those waves would have traveled before freezing, that frozen distance functions as a known, fixed ruler baked into the universe itself, one that corresponds to a present-day co-moving scale of roughly 490 million light-years. Measure how large that ruler appears to us at different distances and different points in cosmic history, and you can work out exactly how much space has expanded in between. An independent check on the universe's expansion history that has nothing to do with Cepheid stars, exploding supernovae, or the cosmic microwave background, a genuinely separate line of evidence pointing at the same underlying question. DESI isn't the first instrument to attempt something like this either. It's the latest in a lineage stretching back decades. The 2-degree field galaxy redshift survey, completed in the early 2000s, mapped roughly 200,000 galaxies, a huge achievement at the time. The Sloan Digital Sky Survey, running for years afterward, pushed that number into the millions and became one of the most cited datasets in the history of astronomy. DESI extends that same basic lineage by an order of magnitude again, and each generation of survey has meant a sharper picture of both the cosmic web's structure and the expansion history hidden inside it. The byproduct of all that galaxy mapping is something worth seeing in its own right. Plot the position of every galaxy DESI catalogues in 3 dimensions, and instead of a random scatter of points, a genuine structure emerges. Long filaments of galaxies, strung together like threads, wrapping around enormous, mostly empty voids, forming what astronomers call the cosmic web. Matter in the universe isn't spread evenly, it's woven, gravity slowly pulling gas and galaxies together along the densest filaments over billions of years, while the voids between them grow steadily emptier. DESI's 3-dimensional map isn't just a tool for measuring dark energy, it's the largest single portrait of that woven structure ever assembled, tracing the same cosmic architecture all the way back across 11 billion years of the universe's history. A structure so vast that individual galaxies, entire galaxies, register as little more than single pixels in the final picture. All of modern cosmology, including everything in this video, rests on an assumption physicists call the cosmological principle, the idea that on the largest possible scales, the universe looks roughly the same in every direction and from every vantage point, with no special location and no preferred direction anywhere. It's a foundational assumption, not something anyone has proven beyond doubt, and every so often, a new study briefly threatens to overturn it. One recent example involved a widely covered paper that used the same DESI dataset this section is built on to argue that cosmic filaments stretched farther and pointed in more consistently preferred directions than the cosmological principle should allow, a result that, if it had held up, would have undermined not just DESI's dark energy findings, but essentially every large-scale cosmological calculation built on the assumption of a uniform universe. It generated real excitement for a while, until outside physicists reviewing the underlying calculations found the authors had made a basic error in how they measured the scale of the structures involved, and the surprising result didn't hold up. It's a small, useful reminder of exactly the kind of self-correction we described earlier. An extraordinary claim got made, got checked by people with no stake in the outcome, and got walked back once the math didn't survive scrutiny. On March 17th and 18th of 2025, the DESI collaboration released a new batch of results, and the headlines that followed were dramatic for a reason. This wasn't the collaboration's first release either. An earlier round of DESI results in 2024 had already hinted at the same pattern, and this second, larger release, built on nearly 3 times the data, was watched closely across the field, specifically to see whether that early hint would strengthen or quietly disappear the way many first-year surprises in cosmology tend to. It didn't disappear. Taken entirely on its own, DESI's data is still consistent with the standard model, the idea that dark energy behaves as a fixed, unchanging cosmological constant, exactly as Einstein's original equations allowed for. But when researchers combined DESI's map with other major datasets, the cosmic microwave background, distant supernovae, and a technique called weak gravitational lensing, a pattern started to emerge, suggesting dark energy might not be constant at all. It might be weakening over time. Weak gravitational lensing deserves a quick explanation of its own, because it's one of the stranger tools in a cosmologist's kit. Massive objects, galaxy clusters especially, bend the fabric of space around them, a direct consequence of Einstein's general relativity, and that bending distorts the path of any light passing nearby, including light from galaxies sitting far behind the cluster from our point of view. Light bending around mass isn't a new idea invented for this purpose either. It's the same basic effect famously confirmed back in 1919, when astronomer Arthur Eddington measured starlight bending around the Sun during a total solar eclipse, one of the first major experimental confirmations of general relativity itself, turning Einstein almost overnight into a household name. In the most extreme cases, this produces dramatic, obvious arcs and rings, but far more often the distortion is subtle, a slight stretching and shearing of background galaxy shapes that only becomes visible statistically once you average the tiny distortions across thousands or millions of galaxies at once, because that distortion depends on how much mass, including dark matter, sits between us and those background galaxies, and on how far that light has traveled through an expanding universe to reach us. Weak lensing gives cosmologists an entirely independent way to map out both the distribution of matter and the expansion history of the cosmos, a check that doesn't rely on standard candles or sound waves frozen into the CMB at all. Will Percival, one of DESI's co-spokespeople and a professor at the University of Waterloo, put it plainly when the results came out. "We're guided by Occam's razor," he said, "and the simplest explanation for what we see is shifting." Occam's razor, for anyone unfamiliar with the phrase, is the old principle that when you're choosing between competing explanations for the same evidence, the simplest one, the one requiring the fewest extra assumptions, is usually the better bet. Percival's point was that the simplest available explanation for everything DESI and its partner datasets were seeing had itself quietly changed, from a fixed cosmological constant to something that evolves. He went on to say it's looking more and more like scientists may need to modify the standard model of cosmology to make all these different datasets agree with each other, adding that evolving dark energy seems like a promising direction. If dark energy really has been getting weaker over cosmic time, rather than holding steady the way physicists have generally assumed since 1998, that would represent one of the biggest shifts in cosmology in a generation, on top of a mystery, the Hubble tension, that was already unresolved. It's worth pulling back the curtain on exactly how researchers put a number on a claim like dark energy weakening, because the specific tool involved matters for how confident anyone should be. Cosmologists describe dark energy's behavior using something called an equation of state parameter, written simply as W, which captures the relationship between dark energy's pressure and its density. If W equals exactly -1, dark energy is behaving as a true, unchanging cosmological constant, precisely the assumption baked into the Standard Model since Einstein's own equations. If W drifts away from -1, or changes over time, dark energy is no longer constant, it's dynamical, sometimes given its own name in the technical literature, quintessence, a term borrowed from ancient philosophy's mythical fifth element, now repurposed to describe a dark energy field that can genuinely evolve as the universe ages. The most common way researchers test this is a formula called the CPL parameterization, built by Michel Chevalier and David Pulaski in 2001 and extended by Eric Linder in 2003, which breaks dark energy's behavior into two numbers, W0, its value today, and WA, how fast that value is changing as the universe expands. Set W0 to -1 and WA to 0, and you're right back to the plain, boring, unchanging cosmological constant. DESI's results, combined with supernova and CMB data, keep landing on values where W0 sits above -1 and WA sits below 0, mathematical shorthand for dark energy having been stronger in the past and weaker now. Here's the honest complication, the part that keeps a lot of cosmologists from popping champagne just yet. How strong that signal looks depends heavily on which specific mathematical parameterization you choose and which combination of datasets you feed into it. Some analyses combining DESI's baryon acoustic oscillation data with one particular supernova catalog report a deviation from the standard cosmological constant as high as 3.9 standard deviations, a genuinely striking result. But other equally valid statistical treatments of essentially the same underlying data, once you account for how different cosmological parameters interact and correlate with each other, bring that same evidence down below 2 standard deviations, a much softer, far less conclusive signal. Multiple papers in the technical literature explicitly warn against treating this as a confirmed detection of new physics, precisely because the result is, in their words, parameterization dependent. It's exactly this kind of sensitivity, results shifting depending on which statistical lens you look through, that would come roaring back into the spotlight later that same year, when the Yonsei team's much bolder deceleration claim ran into the same fundamental question: does the underlying physics actually change, or does the answer change depending on how the data gets sliced? Not everyone is convinced, and that's worth being honest about. Some physicists and science communicators have pushed back on how confidently these results have been reported, pointing out that DESI's own galaxy map by itself doesn't demand this conclusion, and that the strongest evidence for evolving dark energy only shows up once you start blending in supernova datasets that may carry their own internal calibration mismatches between nearby and distant samples. Astronomer Virginia Trimble and several colleagues, writing about the DESI results in April of 2025, reached for 2 older quotes to frame their caution. First, invoking the physicist Lev Landau's dry observation that cosmologists are often in error but never in doubt, and then Carl Sagan's familiar reminder that extraordinary claims require extraordinary evidence, adding plainly that on the question of evolving dark energy, we are not there yet. University of Michigan physicist Dragan Hutera, weighing in on a related and even more dramatic claim later that year, put the same underlying caution more bluntly still. Extraordinary claims require extraordinary evidence, he said, adding that he didn't feel the research in question had cleared the bar needed to overturn the currently favored model. In other words, the jury is still out, actively and publicly, among the people best qualified to judge it. What nobody disputes is that the data keeps getting bigger and more precise, and upcoming missions are specifically designed to settle questions like this one. The European Space Agency's Euclid Space Telescope, already collecting data since its 2023 launch, is mapping the shapes and positions of billions of galaxies across a huge swath of sky, specifically to nail down weak lensing and large-scale structure measurements with far greater precision than before. NASA's Nancy Grace Roman Space Telescope, named for the astronomer often called the Mother of Hubble for her role championing that earlier telescope decades before it ever launched, is expected to join the effort later this decade, built with a wide enough field of view to survey enormous areas of sky in a fraction of the time older telescopes would need, adding yet another independent line of evidence to weigh against DESI's results. Both missions were conceived, in large part, specifically because of the kind of uncertainty this video has been describing, built by people who already knew, years in advance, that the Hubble tension and the nature of dark energy would still be open questions by the time their instruments were finally ready to fly. For now, the honest answer is that we don't fully know whether the force pushing our universe apart has always been exactly the same strength, or whether it's been quietly changing the entire time, and that we've only just recently developed the tools sharp enough to even ask the question properly. And then, just months after this script's research was compiled, the story took an even sharper turn, one that shows exactly how this kind of science actually gets settled, argument by argument, out in the open. On November 6th of 2025, a team from Yonsei University in South Korea, led by Professor Young-Wook Lee, published a study going considerably further than DESI's cautious hints. Lee's team argued that Type ER supernovae, the exact same standard candles that revealed cosmic acceleration back in 1998, weren't as standard as everyone had assumed. Remember, the whole method depends on every one of these exploding white dwarfs releasing essentially the same amount of energy, treating them as interchangeable light bulbs of known wattage scattered across billions of years of cosmic history. Lee's team's claim was that this assumption quietly breaks down, that supernovae born from younger progenitor stars burn intrinsically fainter than those from older stars, even after all the usual corrections astronomers apply, introducing a subtle bias into decades of distance measurements, one that would have crept in more heavily toward the ends of cosmic history, where progenitor star populations differ most from our own cosmic neighborhood. Correct for that bias, combine the adjusted numbers with DESI's baryon acoustic oscillation data and the cosmic microwave background, and Lee's team concluded the standard model wasn't just strained, it was ruled out with overwhelming significance. Their claim wasn't merely that dark energy might be weakening, it was that the universe's expansion had already stopped accelerating altogether and had entered an outright decelerating phase, right now, in the present era. Professor Lee didn't hedge when describing the result. Our study shows that the universe has already entered a phase of decelerated expansion at the present epoch, he said, and that dark energy evolves with time much more rapidly than previously thought. He went further in a separate comment, saying dark energy is getting weirder and weirder, but there is no good theory that can explain this very weird behavior, so I think we are missing something. If Lee's team was right, it meant the foundational discovery behind Perlmutter, Schmidt, and Rees's 2011 Nobel Prize, the very finding this entire video has been built around, needed to be fundamentally reconsidered. It did not take long for a response to arrive, and the response came from about as credible a source as Cosmology has to offer. In June of 2026, a team led by Dr. Phil Wiseman at the University of Southampton published a reanalysis of Lee's data and methodology, and this team included, as co-authors, Adam Rees and Brian Schmidt themselves, two of the three scientists who had actually made the original 1998 discovery being challenged. Wiseman's team went back through the supernova data, examined where the proposed age bias correction had gone wrong, and concluded the controversy stemmed from a misunderstanding of the data rather than a problem with the universe itself. The previous and well-accepted measurements were, in fact, fine, Wiseman said, and our reanalysis confirms the universe's expansion is continuing to accelerate exactly as the standard model predicts. As of the most recent evidence available, the challenge to cosmic acceleration appears to have been resolved in favor of the original 1998 result, though Lee's team has indicated they intend to keep testing the idea using future data from the Vera Rubin Observatory, a new ground-based telescope in Chile built specifically to photograph the entire visible sky over and over every few nights for a full decade, and expected to catch thousands of new supernovae of exactly the kind at the center of this dispute, so this particular chapter may not be fully closed. There's something worth sitting with in that 7-month back and forth, independent of who turns out to be right in the end. A team of scientists published a serious, peer-reviewed challenge to one of the most celebrated discoveries in modern physics. The scientific community didn't dismiss it or bury it. It got tested, argued over, and eventually, the two men whose careers and Nobel Prize rested on the original result came back with their own data and their own analysis to defend it in public, in a journal where anyone could check their work. That's not a flaw in how science operates. That is, in fact, exactly how it's supposed to work. Disagreement dragged out into daylight and settled with evidence rather than with authority or reputation. Now let's get to the part of this that tends to break people's brains a little, because it's the part where the phrase in our title, "faster than we can ever follow," stops being a figure of speech and starts being a literal, measurable fact. The universe is 13.8 billion years old. Simple enough, and yet the observable universe, the maximum distance we can actually see in any direction, stretches out to roughly 45 billion light-years. Notice that 45 is a lot bigger than 13.8. That should sound like a contradiction, and it would be, except for one detail we already covered. While that ancient light has been traveling toward us for nearly 14 billion years, the space it's been traveling through has itself been stretching the entire time. Think of it like an ant walking across a slowly inflating balloon, starting from one point and crawling steadily toward another. If the balloon weren't inflating, the ant's traveled distance and the gap it crossed would match up perfectly. But because the balloon keeps stretching underneath the ant's feet the entire time it's walking, the actual gap between where the ant started and where its destination has drifted to ends up considerably larger than the distance the ant physically walked. The light left its source closer to us than it is now, and the expansion of space during its journey stretched that gap out to 45 billion light-years by the time the photons finally arrived at our telescopes, even though the light itself only spent 13.8 billion years in transit. This boundary has a technical name, the particle horizon, sometimes called the co-moving horizon, and it marks the outer edge of everything we can currently detect, the entire observable universe, today, at this exact moment. That 45 billion light-year figure is a radius, not a total width, meaning the full diameter of the observable universe, edge to edge in every direction, comes out to roughly 93 billion light-years, a sphere so large that Earth, the Sun, the entire Milky Way, and every galaxy DESI has ever catalogued amount to a barely noticeable smudge somewhere near its middle. But there's a second, much harsher boundary, and this one doesn't get bigger and more generous over time the way the particle horizon does. It's called the cosmological event horizon, and it currently sits somewhere around 17 to 18 billion light-years away. Here's what makes it different, and honestly, worse. Any light being emitted right now, from any object beyond that 17 or 18 billion light-year line, will never, under any circumstances, reach Earth. Not in a million years, not in a trillion, not ever, no matter how long we wait or how sensitive our instruments become. The space between us and that light is expanding too fast for the light to ever close the distance. It's not that the signal is faint or hard to detect, it's that the signal is mathematically, permanently incapable of arriving. There's actually a third boundary worth knowing about, sitting between those two, called the Hubble sphere or the Hubble radius. This is the distance at which a galaxy's recession velocity, purely from the stretching of space, equals the speed of light exactly. Inside that sphere, galaxies recede slower than light. Outside it, they recede faster. Crucially, that doesn't mean their light can never reach us, because as we covered earlier, a photon can still be emitted from just outside the Hubble sphere and eventually cross back inside it as the sphere itself shifts over cosmic time, slowly making its way toward Earth across billions of years. It's really only the cosmological event horizon, that far more distant, harder boundary, that represents an absolute point of no return for any signal, ever. Physicists sometimes visualize this using something called a light cone, essentially a diagram tracking every possible path light could take toward an observer across the entire history of the universe. Picture our own position as a single vertical line running through time, and picture the light we're receiving right now, from every distant galaxy, tracing curved paths back through billions of years toward us. In the most distant past, those paths look roughly cone-shaped, the way you'd expect. But trace them back far enough, and the shape distorts into something closer to a teardrop, narrowing and curving in a way that reflects a strange, almost counterintuitive fact. The very farthest light we can see today was actually receding from us, moving away, for the first several billion years of its journey, before the changing balance between expansion and the shrinking distances involved eventually let it start closing the gap toward us instead. Even the fundamentals of how light reaches us across cosmic time turn out to be stranger than the simple picture of a beam traveling in a straight line from source to observer. This isn't the same kind of horizon as a black hole's event horizon, but it functions with a similar kind of finality. Because our universe's expansion is accelerating, driven by dark energy, this cosmological event horizon isn't standing still, and it isn't slowly retreating to reveal more of the cosmos to us over time either. Calculations suggest it will keep growing for a while, but it will eventually level off, asymptoting toward a fixed distance of around 60 billion light-years. Because as dark energy's push wins out more and more decisively over gravity, the region we could ever theoretically receive a signal from approaches a hard limit. Beyond that limit, forever, is simply off the table. Some estimates, and this is worth flagging as an approximation rather than a precisely nailed-down figure, suggest that somewhere around 94% of the universe already sits beyond that cosmological event horizon, permanently unreachable, no matter what we build or how long our species survives. One estimate even puts a number on how fast we're losing ground, suggesting something like 160 billion stars, spread across countless galaxies, slip across that boundary every single year, crossing from theoretically reachable to forever gone. And here's the detail that makes this feel less like a sudden door slamming shut, and more like a slow fade. Galaxies crossing this horizon don't blink out of existence, or vanish instantly from our view. Their light simply gets stretched further and further toward longer, redder wavelengths as the expansion between us and them accelerates, growing dimmer and dimmer, redder and redder, until eventually it becomes too faint and too stretched to detect at all. Nothing dramatic happens. Nothing explodes. The universe just quietly, continuously, permanently pulls itself apart, piece by piece, while we watch. It helps to put a number like 17 billion light-years next to something we actually have real experience with. The fastest spacecraft humanity has ever built, the Voyager probes, launched back in the 1970s and still transmitting faint signals from interstellar space today, travel at roughly 38,000 miles per hour relative to the Sun. Even NASA's Parker Solar Probe, which set an entirely different kind of speed record by diving repeatedly through the Sun's outer atmosphere and at its closest approach, reaches speeds of several 100,000 miles per hour. The fastest human-made object ever built still amounts to a rounding error against light speed, which moves at roughly 670 million miles per hour. At any of these speeds, reaching even our nearest neighboring star system would take on the order of thousands to tens of thousands of years. Reaching the edge of the cosmological event horizon at any of these speeds isn't a matter of tens of thousands of years, or millions, or even billions. It simply never happens, not because the trip is too long, but because the destination itself is retreating away from any traveler faster than any signal, of any kind, moving at any speed up to the speed of light, could ever close the gap. This is also, incidentally, exactly why an instrument like JOST has to observe primarily in infrared light, rather than the visible light your eyes are built for. The most distant, most ancient galaxies have had their original light stretched by cosmic expansion so dramatically, redshifted so far, that visible light emitted at the dawn of galaxy formation arrives here today as infrared radiation, wavelengths your eyes were never built to see, invisible unless you build a telescope specifically tuned to catch it. So where does all of this actually lead? If the current models hold, and that's an important if, given everything we just covered about dark energy possibly evolving, the future of the universe unfolds on timescales so long they stop feeling like numbers and start feeling more like abstract concepts. Physicists Fred Adams and Greg Laughlin laid out a framework for thinking about exactly this in a book called The 5 Ages of the Universe, organizing the entire future of the cosmos into 5 broad chapters. A structure worth borrowing here because it gives these unimaginable timescales at least some kind of shape. We are living, right now, in what they call the Stelliferous era, the age of starlight, the period during which most of the universe's energy comes from ordinary nuclear fusion inside stars. Everything else we're about to describe happens after this era ends. Somewhere around 100 million years from now, by some estimates, galaxies outside our own local group will have receded far enough that we can no longer observe them from the Milky Way at all. On a separate, much more near-term track, our own galaxy is due to merge with the Andromeda galaxy, gravitationally bound to us and therefore immune to this whole expanding away story, becoming one single combined galaxy in the process. Push further out, into the range of 1 to 100 trillion years from now, and the universe simply runs out of raw material. Star formation depends on gas clouds collapsing under gravity, and that gas supply is finite. Once it's exhausted, no new stars are born, ever again, closing out the stelliferous era we mentioned a moment ago. Along the way, other transformations are unfolding on their own separate timelines. Our own sun, roughly 5 billion years from now, will swell into a red giant, engulfing Mercury and Venus, and quite possibly Earth along with them, before shedding its outer layers entirely and settling down as a slowly cooling white dwarf. That's a comparatively near-term event, cosmologically speaking, a footnote against the trillion-year timescales we're describing for the rest of the universe. Around 120 trillion years out, even the longest-lived, most fuel-efficient stars, still burning at that point, finally go dark. What's left after that is the second of the 5 chapters, called the Degenerate Era, a universe populated only by stellar remnants, white dwarfs slowly cooling, neutron stars, and black holes, with galaxies themselves eventually breaking apart as their components disperse or spiral into the supermassive black holes at their centers. From there, the timescales stretch into territory that's almost impossible to hold in your head. Some theoretical physicists predict that even the stellar remnants left over after star formation ends won't last forever in their current form. According to a theoretical process called proton decay, never yet observed but predicted by some extensions of particle physics, the protons that make up ordinary matter might themselves eventually break apart. Over a timescale, some estimates place around 10 to the 34th power years, an almost meaninglessly large number, at which point even the cold, dead husks of stars would slowly disintegrate down to their most basic particles. This remains genuinely speculative, since proton decay has never actually been detected in any experiment, but it's a serious hypothesis, taken seriously enough that physicists have built entire timelines around what would happen if it's true. After that, on the kind of extraordinarily long time frames discussed in the theoretical physics literature, this leads into the 4th of the 5 chapters, sometimes called the Black Hole Era, a period during which black holes themselves are expected to slowly evaporate, radiating away their mass through a theoretical process called Hawking radiation, named for physicist Stephen Hawking, who first proposed it. Hawking radiation has never been directly detected either. It's simply predicted to be so faint that no instrument built so far could possibly measure it. But if the theory holds, every black hole in the universe eventually shrinks and vanishes. The timescales involved are almost comically long, even by the standards of everything else in this video. A black hole roughly the mass of our sun would take something like 10 to the 67th power years to fully evaporate. The truly enormous supermassive black holes, sitting at the centers of galaxies, by contrast, would take something closer to 10 to the 100th power years, a number with a name, a googol, meaning a 1, followed by 100 zeros, to disappear completely. Once that happens, once every black hole has finally evaporated away, the universe enters its 5th and final chapter, sometimes simply called the Dark Era, in which there is, according to this model, nothing left. No stars, no planets, no black holes, no protons, nothing but an unimaginably thin, cold spray of photons, and the lightest possible particles, spread across a universe that never stops expanding, forever. This end state has a few different names depending on who's describing it. Heat death, the big freeze, the big chill. All of them point to the same basic picture, a cosmos that has reached maximum entropy, every bit of usable energy exhausted, temperature settled just barely above absolute zero, forever, with nothing left to happen ever again. That's the leading, most favored outcome given what we currently know, but it's worth being upfront that it isn't the only scenario still on the table. If dark energy's repulsive push doesn't just stay constant, but actually grows stronger and stronger without any limit, something scientists call the Big Rip becomes possible, a far more violent ending where the accelerating expansion eventually overwhelms not just the space between galaxies, but the gravity holding galaxies together, then the gravity holding solar systems together, and finally, even the forces holding atoms themselves intact, tearing the very fabric of everything apart. The idea was first formally proposed in 2003 by physicist Robert Caldwell, and later reviewed and extended by other researchers examining exactly what kind of dark energy behavior would be required to trigger it. Data from surveys like Wigglesy haven't ruled this scenario out entirely, but they do push it into an extraordinarily distant, almost inconceivably far future if it happens at all. There's also the Big Crunch, the far older idea, predating the discovery of acceleration entirely, that expansion could someday reverse, and the universe could collapse back into itself under its own gravity, potentially ending in a reversal of the Big Bang, a single, impossibly dense point once again. This scenario looks increasingly unlikely, given that everything we've measured points toward acceleration rather than any kind of slowdown. But it hasn't been mathematically eliminated either, especially if the DESI hints about weakening dark energy turn out to represent dark energy eventually flipping from a repulsive to an attractive influence somewhere in the deep future, something current data cannot rule out. And this is exactly why that DESI result from March of 2025 matters so much more than a single data release usually would. If dark energy really has been weakening over cosmic time, the way some of that combined data hints it might be, then the entire long-range forecast for the universe, heat death, Big Rip, whichever outcome you'd bet on, gets thrown back into question. We are, right now, in the strange position of having mapped out several plausible endings for everything that exists, while still not being entirely sure which force is actually driving us toward any of them, or whether that force has been quietly changing its mind the whole time. It's worth pausing here and thinking about what any of this actually means for a person alive right now, watching this on a screen, on a planet that is itself just a speck orbiting an unremarkable star in the outer suburbs of one galaxy among what is, by current estimates, hundreds of billions of galaxies within the observable universe alone. Every single one of those galaxies you could theoretically point a powerful enough telescope toward tonight is, at this moment, drifting a little farther away than it was yesterday, and every night that passes, a little more of the cosmos slips permanently past that 17 or 18 billion light-year line and out of reach forever. That's not a metaphor. That's the literal, ongoing, measurable state of the universe you're sitting inside of right now. There's something almost humbling about the timescales involved here too. Human civilization, in any recognizable form, is maybe 10 or 12,000 years old. Modern astronomy, the kind capable of even asking these questions, is a few hundred years old at most. The precise measurements that produced the numbers in this video, the Hubble tension, the DESI dark energy results, the cosmological event horizon distance, all of that has emerged in roughly the last 3 decades, an absolute blink of an eye set against a universe that is 13.8 billion years old and, according to current models, has trillions upon trillions of years left ahead of it before anything resembling an ending arrives. We are, in a very real sense, a species that showed up extremely late to a party that started unimaginably long ago, and we're trying to reconstruct the entire guest list, the entire timeline, and the entire eventual outcome of the evening, using nothing but the faint, stretched-out light that happens to still be reaching us. Every telescope pointed at the sky is, in that sense, a kind of time machine, incapable of showing anyone the present moment anywhere but here, only ever showing the past, layered past on top of past, all the way back to a moment 380,000 years after everything began. There's also something worth noticing in how often this story involves people being wrong, publicly, and correcting course without it destroying anyone's career or credibility. Einstein was wrong about a static universe, and said so, or at least behaved as though he knew it, dropping the fix he'd built to defend the wrong idea. Two rival teams in the 1990s set out to confirm one thing and ended up proving the opposite. A supposedly settled 1998 discovery got seriously, publicly challenged in November of 2025 by researchers with real data and a real argument, and instead of the field circling the wagons to protect a Nobel Prize, it got tested in the open by the very people whose prize was on the line, and the matter got resolved with new analysis rather than old authority. That pattern, propose, test, get challenged, defend or revise, repeat, isn't a flaw in how cosmology works. It's the entire reason any of the numbers in this video are worth trusting in the first place. It's also worth noticing what separates the well-tested parts of this story from the speculative parts, because that line matters more than it might seem. Hubble's law can be checked by anyone with access to a telescope and a spectrograph. The cosmic microwave background sits there, physically, waiting to be measured by any instrument sensitive enough to catch it, which is exactly how three separate generations of satellites managed to refine the same basic signal decades apart. The 1998 acceleration discovery got checked and rechecked and challenged and defended, with actual data changing actual minds along the way. Eternal inflation and the multiverse, by contrast, currently offer no comparable path to being checked at all. No observation that could come back and prove the idea wrong. That's not a knock against the physicists who take it seriously. The mathematics genuinely follows from well-tested ideas about inflation, but it is the honest reason this video treats the multiverse as a fascinating possibility rather than a discovery, while treating the accelerating expansion of the universe as settled fact. A good scientific idea has to be able to fail a test. Most of what you've heard in this video has faced that test, repeatedly, and survived. And yet, somehow, that's exactly what's been accomplished, piece by piece, disagreement by disagreement, correction by correction. A priest working out equations in French. Two rival teams chasing the same wrong hypothesis and stumbling into a right one instead. Two engineers who thought pigeon droppings were interfering with a satellite antenna and ended up detecting the echo of creation itself. A spectroscopic instrument bolted onto a telescope in the Arizona desert right now, in this decade, quietly gathering the data that might finally explain why two completely different ways of measuring the same fundamental number keep refusing to agree. Before we close this out, it's worth laying all these numbers side by side, because scattered across an hour of narration they're easy to lose track of, and together they tell a genuinely coherent story. The universe is 13.82 billion years old, made up of roughly 68% dark energy, 27% dark matter, and just 5% the ordinary matter that makes up every star, planet, and person. It's expanding at somewhere between 67 and 74 kilometers per second per megaparsec, depending on which half of the universe's history you measure it from, a gap nobody has explained. That expansion is accelerating, not decelerating, confirmed independently by supernovae, by the cosmic microwave background, by baryon acoustic oscillations, and, as of 2026, reconfirmed once more after a serious direct challenge to the original result. The observable universe stretches 45 billion light-years in every direction, even though light has only had 13.8 billion years to travel, because the space it crossed kept stretching the entire time. Beyond about 17 to 18 billion light-years sits a cosmological event horizon, a boundary past which light emitted today will never reach us, not ever, regardless of how long we wait. Roughly 94% of the universe, by some estimates, already sits beyond that line. And out past the edge of anything testable at all, a serious minority of physicists suspect that our entire observable universe might be one bubble among an unknown, possibly endless, number of others, an idea nobody has yet found a way to check. Every single one of those numbers came from somewhere specific. A Belgian priest's overlooked 1927 paper, a Harvard photometrist's overlooked notebooks, a mule driver turned observer, a horror movie watched by three friends in 1946, an accidental discovery involving pigeons, two competing teams chasing the wrong hypothesis, a Nobel Prize, a tension nobody can explain, a telescope finding galaxies too massive to exist yet, and an instrument in the Arizona desert, currently rewriting the ending. That's the actual state of humanity's best understanding of the universe's expansion, as precisely as it can be stated today, acknowledged uncertainties and all. There's one more thing worth sitting with before we close, an old idea that sits quietly underneath everything else in this video. It's sometimes called the Copernican principle, after Nicolaus Copernicus, the 16th century astronomer who first argued, at real professional and personal risk in his era, that Earth wasn't the fixed center of the solar system, and in its modern form, the principle simply says that we don't occupy any special place in the universe either. Every galaxy, from its own point of view, sees itself sitting at the apparent center of its own observable universe, surrounded by its own particular horizon, its own particular slice of everything reachable. We are not special for being at the middle of what we can see. Every single observer, anywhere in the cosmos, gets that same illusion, the same 45 billion light-year bubble stretching out around them in every direction, the same cosmological event horizon, quietly closing in past that. It's a strange kind of universal fairness, a horizon everyone gets, and a horizon nobody can ever cross. There's a quiet comfort buried somewhere in that fact too, even if it wasn't designed to comfort anyone. Whatever else remains unresolved about dark energy, about the Hubble tension, about the multiverse, or the ultimate fate of everything, the basic experience of standing on a small planet and looking out at a universe that seems to stretch away from you in every direction, forever, is not unique to us, and never has been. It's the same experience any observer, anywhere, watching any sky, would have. In a universe this large, that shared, ordinary strangeness might be the closest thing to common ground there is, a horizon drawn fresh around every single observer who has ever looked up and wondered how far it all really goes. Step back and look at the whole shape of this story, and something remarkable stands out. It took less than 100 years to go from not knowing the universe was expanding at all, to arguing over whether the very force driving that expansion has been changing its strength across billions of years of cosmic history. Henrietta Leavitt spent years hunched over photographic plates in a Harvard office, working out how to measure distance using nothing but the pulse rate of dying stars, and died before anyone thought to properly credit her for it. Vesto Slipher measured the first hints of cosmic recession with nothing but starlight and a spectrograph. Georges Lemaitre worked out the math in French and let Hubble take the spotlight without complaint. Einstein himself patched his own equations to hide a truth those same equations were trying to tell him, then dropped the patch, and decades later watched, or would have watched, as that same patch became essential again for an entirely different reason. Two rival teams set out in the 1990s to measure how quickly gravity was slowing everything down, and instead proved the opposite was happening. A Bell Labs antenna, meant for satellite calls, picked up the actual echo of the Big Bang because two engineers refused to stop chasing an unexplained hum, even after clearing pigeons out of the equipment. A space telescope now sits 1 million miles from Earth, staring so far back in time that it's finding galaxies that shouldn't exist yet, according to the very models built on everything else in this video. And right now, in this decade, a spectroscopic instrument bolted to a telescope in Arizona is quietly suggesting that everything cosmologists have assumed about dark energy for the last 25 years might need to be rewritten. Just months later, that same rewrite got its own serious public challenge from a team on the other side of the world, and just months after that, the two Nobel laureates whose careers were on the line showed up with fresh data to defend their own life's work in the open. Somewhere further out on the theoretical edge of all this, a small number of physicists are seriously entertaining the idea that inflation never fully stopped anywhere, that our entire observable universe is one bubble among an uncountable, perhaps infinite, number of others, forever cut off from every one of them, an idea nobody currently knows how to test, sitting right alongside a Hubble tension that very much can be tested and still refuses to resolve. None of that changes the basic, almost uncomfortable fact we opened with. Galaxies really are receding from us faster than light can ever cross the growing gap between us. There really is a boundary, sitting somewhere around 17 or 18 billion light-years out, past which light being emitted at this very moment will never, ever reach Earth, regardless of how long our species survives, or how good our telescopes eventually get. The universe is not just big. It is actively, continuously outrunning our ability to ever fully know it, expanding faster than any signal, any spacecraft, any future civilization could ever hope to follow. If you want to keep track of how this particular argument develops, there are a handful of names worth watching. Euclid and the Nancy Grace Roman Space Telescope will keep adding precision to the Hubble tension over the rest of this decade. DESI will keep releasing new data releases, each one either strengthening or weakening the case for evolving dark energy. And the Vera Rubin Observatory, once its decade-long survey gets rolling, is likely to produce exactly the kind of enormous, high-quality supernova sample that could finally settle the argument the Yonsei and Southampton teams are currently having. None of this is finished. Most of it, honestly, is just getting started, and whatever the next chapter turns out to be, it will almost certainly come from data that doesn't exist yet, gathered by an instrument that, as of this video, is either still being built or still being dreamed up on a whiteboard somewhere. We've spent a century catching up to that idea, piece by piece, mistake by mistake, discovery by discovery, and we're still not finished. Somewhere out past the edge of everything we've measured, past the 17 or 18 billion light-year line, past the 94% of the cosmos already gone from us, the universe keeps expanding, regardless of whether anyone is watching, regardless of whether we ever manage to fully explain it. If anything, the last few years have made it clearer than ever that there's still a great deal we don't understand about the force quietly pulling everything apart. Right now, while you finish watching this sentence, while the light from 100 billion galaxies keeps stretching a little farther out of reach, one quiet moment at a time,